Welcome everyone again to our webinar today. We're going to be getting in depth on editing ECG for high frequency heart rate variability. My name is Eric Morgan. I'm the president and CEO of MindWare Technologies, and I will be your presenter today. So first things first, I want to talk about general agenda, what we're going to be covering throughout this session. It's going to be a 90-minute session. The first hour will be a lot of me talking, and then the last 30 minutes, you'll be able to ask questions, and I'll do my best to answer all of them that we can get to within that time period. Of course, you are welcome to ask questions throughout the entire webinar. There's a questions panel in the GoToWebinar interface that you can use to ask us a question. It can be about anything that you see in the presentation, anything you want to learn more about, any related questions or topics. Feel free to ask questions, and we'll get to them, like I said, during the Q&A period at the end. And just so everyone knows, this webinar will later be available for rewatching on our YouTube channel. We'll be sending out a link to that to everyone that is attending today, so no need to furiously write down notes or anything like that. You're going to be able to rewatch this as much as you'd like to. So we're going to start by defining a few terms that come to mind for when we're editing data for high frequency HRV. What is high frequency HRV? What is RSA? Things like that. Then we're going to talk a little bit about ECG, electrocardiogram processing and editing in general, some general rules that we follow, some steps that we take to optimize ECG for editing. And then we're going to dive into the application itself. So we're going to be talking about a lot of editing techniques today that would apply to any ECG editor that you're using, whether it's a MindWare tool or not. But given this is a MindWare webinar, we're going to be using the MindWare HRV analysis application to demonstrate the various techniques that I'm going to talk about. And like I said, at the end, we'll save plenty of time for questions and answers. So first things first, like I said, we're going to define a few terms that are important to understand when we're talking about editing for this type of analysis. And the first is the ECG, or if you're German, EKG. It's commonly used in the literature, EKG instead. It stands for the electrocardiogram. And what we're measuring here is the electrical activity of the heart. And what's shown here on the slide is a typical depiction of a lead 2 configuration ECG. And there are a few components that I think are important to at least recognize when you're looking at an ECG signal, because it can be really helpful when it comes time to edit the signal to identify where there may be noise or there may be abnormal beats. So whether or not you understand exactly what each one of these landmarks mean, it's important to just know, generally speaking, what a single cycle of ECG should look like. And so that's depicted right here. And again, this is in a lead 2 configuration. So that's where the negative lead is on the right clavicle, the positive lead is on the lower left rib, and we're going to be looking at that vector of the heart. And that's particularly important because that's what's going to produce the morphology that we see here, and it's going to produce the most consistent morphology by which to do this type of data analysis. So that's the configuration that I would recommend we use in this instance. So just want to take a quick second to talk about a few of these components, again, because they're going to be important for us to recognize later. So the cycle generally starts with a P wave. We can see that as a small positive deflection on the left-hand side here. That is atrial depolarization, and we will typically see it, but we won't always see it. So it's important to at least know that it should be there, but depending on electrode placement, on conditions during the experiment, we may or may not see a clear P wave. But what we should definitely see pretty clearly on a cycle-by-cycle basis is the QRS complex. We can see that as the negative deflection right before we rise to the R peak, and then we descend again to a negative deflection, which is the S wave. This is a very easily observed portion of the ECG signal that we can expect to see on a cycle-by-cycle basis almost always in proper measurement conditions. And again, you don't necessarily need to know exactly what this means. It's measuring ventricular depolarization in technical terms, but for our purposes, what we really want to see is that R peak, that clear and precisely identifiable fiducial point on this cycle by which we can essentially determine beat-to-beat timing. So the R peak is always going to be positive. It can be negative if you swap the leads on accident, but we can very easily swap those back so that it's positive again, just with a single button press in the application. So no worries if it is negative, but by convention, the R peak is typically positive. And then finally, we have repolarization with the T wave following the QRS complex. We're almost always going to see a T wave as well. We don't use it to identify beat-to-beat timing because it is a little more rolling in nature. It has some clinical implications, but for our purposes, we want to see it just so that we can confirm that the beat is indeed normal in timing. And so you're almost always going to see it. And I'll show you some examples later of what a good T wave looks like, and also what one might look like when there's some sort of cardiac arrhythmia taking place. So that is a general representation of an ECG. Like I said, the most important thing, if you took anything away from that, is the R peak being positive and being easily identifiable, because the R peak is what we're going to use to identify beat-to-beat timing. So a couple of the terms I want to define really quickly before we move on are high frequency heart rate variability and respiratory sinus arrhythmia, or RSA. So these terms are often thrown around sort of interchangeably with one another, and they're more or less the same, but only under certain conditions. So I think it's important to just understand the difference between the two and how we should speak about them. So RSA, or respiratory sinus arrhythmia, is the biological phenomena that describes variation in heart rate or beat-to-beat timing that is a result directly of respiration. And we can actually measure high-frequency heart rate variability, HF-HRV as it's abbreviated. That's what we're actually measuring when we're identifying those R peak timings and we're diving down into that specific frequency range. But we can say that high frequency heart rate variability reflects respiratory sinus arrhythmia when we can also confirm that respiration is occurring within those same frequency bands. So you can see here on this plot, we have a respiration on the lower graph and the heart rate power spectrum, which we'll talk about a little later. On the top, this is where we're getting our high frequency heart rate variability statistic. And that's why it's so important that when we're editing for high frequency HRV, we're editing our ECG signal, but the respiration is critical for confirming our assumption that high frequency heart rate variability is in fact reflecting RSA. RSA then reflecting in turn parasympathetic nervous system activity. So that's how we make the connection. That's why we're actually reporting high frequency heart rate variability, but we take the natural log of that statistic as a standardization for respiratory sinus arrhythmia to be reported. So that's the difference between the two. It's important to remember that, and that is what we are really editing for when we work in the HRV application. So with that being said, we understand now the signal that we need to get these statistics, and we know what the statistics actually are. Let's talk about how we get there. We have to get from a raw ECG signal to this representation of high frequency heart rate variability. And there's a few steps that we would take to do that. So we're going to start by optimizing our ECG signal to allow for those R peaks to be clearly and consistently identified on the signal. And we're going to do that by applying some light filters. We'll talk about the specific filters when we get into the HRV application itself, but generally speaking, when we filter our ECG, we're trying to take as little out as possible. And that's generally a rule when we're applying any filters to any physiology data, is we want to preserve as much of the original signal as possible while removing any sort of noise or external frequencies that can make our job more challenging as editors and during analysis. When it comes to ECG, we're really trying to identify that R peak, that fiducial point that is very clearly and consistently identifiable on each cardiac cycle. And so any filtering that we do to the ECG, its only purpose is to make the peak detector's job easier. So we're going to run an algorithm on the ECG at that point to identify the location of each of the R peaks. And once we identify what we believe to be the R peaks, well, then we have to check them for accuracy, for correctness. And like any algorithm, it's not going to be perfect. We're going to do our best, and we use a pretty high quality algorithm in the HRV application. The Shannon energy envelope is the approach we take to R peak detection. We still need some sort of check in there to make sure, does this make sense? Are the peaks that we identified physiologically plausible or not? And if not, we need to bring them to the editor's attention so that we can look a little closer and determine whether or not it should be left or it should be modified in some way. And there are a couple of algorithms we deploy for that as well, which we'll talk about here in a moment. And then finally, we have artifact correction, which is what the primary goal of this webinar is to talk through how, once we get the results of the artifact detection, once we see all these beats for what they are, what can we then do to correct any mistakes that are made? And how can we preserve data even in the presence of noise, even in the absence of a very clear R peak for any given amount of time? And we're going to use the ECG editor in the application to do this. So, okay, those are the steps that we're going to go through, and we're going to talk about those in more detail in a moment. But first of all, why is editing important? Why does it matter that we edit our data for high frequency heart rate variability in particular? Well, here is an example of a segment with no artifact in it. And we can see our RSA is 5.98. That's going to be our indicator of parasympathetic nervous system activity. If we miss one beat in here, we can already see that the RSA value has changed by an entire unit, which is certainly statistically significant. And if we miss several beats, then we can see that we've almost doubled our RSA value. So if we had just gone through and output these statistics without ever looking at the signal, without ever, making the corrections that need to be made, we can really end up with a metric that is not indicative of what was actually going on during a segment. And so it's incredibly important that we do identify each one of these instances of artifact and correct for it. And so there are a few sort of common edits that I'll illustrate really quickly before we get into the actual application. These are the general actions that you would expect to perform when you are going through your editing process. First would be the absence of a peak when you can actually see it. So sometimes because of motion artifact, because of some sort of specific morphology in the waveform, you may not be able to, the peak detector may not be able to actually identify the R peak, but we can see it clearly when we look at the signal. And so in this situation, we would simply insert the R peak in that location. Another sort of common occurrence would be that the peak detector finds a peak on another one of the waveform characteristics. In this case, it looks like a P wave has been identified incorrectly as an R peak. And this can happen again sometimes just based off of cycle by cycle morphology. It just kind of happens. In this situation, you would simply delete this. And then there are those situations where the signal is completely obstructed by some sort of noise. And when that happens, we can't really know for sure where to place our R peak. So we just have to do the best we can. And in this case, we need to estimate where it might have been had we been able to see it. And we would do that simply by inserting a midbeat, which we'll talk about again once we get into the tool. But it's our way of estimating beat location while maintaining a continuous series of R peaks and minimally affecting our statistical output. And there are some rules around how often you can do this as well. Which brings me to the rules. When it comes to HRV, there are just a couple rules that we need to consider when we're doing our edits. The first is the 30-second rule. So that essentially means that we need 30 seconds of contiguous R peaks to calculate RSA for any given segment. And so there are a couple sort of keywords in there that I want to talk about in a little more depth. So why do we need it to be contiguous? Well, any missing or extra beats will appear as additional variability in our beat-to-beat timing. And we won't ignore those because we need to consider them. So RSA can be significantly affected when those are left in or left out. And why 30 seconds? So ideally, as a guideline, when we're looking at any sort of physiological measures, we want to see at least 10 cycles of whatever measure we're looking at to before we trust our statistics fully. And so if you consider sort of the low end of our expected respiration, we would need something like 60 seconds to guarantee that we see 10 respiratory cycles in a segment. So we're always going to recommend that you actually use 60 seconds of data at any given time rather than 30. But this guideline of 10 cycles is really just that. It's a guideline. It's not a hard rule. And quite often, segments representing as little as 5 respiratory cycles can be accepted, are published, are valid. And so 30 seconds is sort of the bottom end of what we would recommend you ever analyze your data. And by analyzing in 60-second segments, we have some more editing options, which we'll see in a moment, where we can remove data portions that are noisy, still end up with at least 30 seconds, and we can still report values on that particular segment. So 30-second rule is the first thing that we need to consider. The next thing we need to consider is the 10% rule. So in my last example, we had this portion of time where we couldn't see an R peak, but we know one should have been there. So we estimated its location. Well, those estimations can add up, and over time, they can start to affect more and more the statistical validity of your output. And so our rule is that no more than 10% of your total peaks can be estimated. And that's just to ensure that we aren't guessing too much and we aren't skewing our results. And if you have to break either one of these rules, then we would generally recommend discarding that particular segment. All right, so with that, we're going to get into the actual application. We're going to walk through some examples of these editing techniques that I just mentioned. We'll talk about filters, we'll talk about all those things. So I'm going to close the PowerPoint presentation and show my application. All right, so the first thing that we're going to do when we open up the HRV application is we're going to choose a file. I'm going to choose example 1 here. And we're going to be asked to map our channels. I'm going to kind of breeze through this because I want to really get into the editing. I don't want to talk a ton about general application usage. There are manuals and blog posts and things on our website that can help you out with all of this stuff. But just really quickly, we just need to tell the application what channel is ECG, what channel is respiration. In this case, for this particular file, we didn't collect a respiration signal, but we can derive respiration from the cardiac impedance waveforms, which is what we're going to do here. And that's actually a great way to look at both parasympathetic and sympathetic nervous system, is to collect actually both ECG and cardiac impedance. In that situation, you don't need a rest belt. You can derive that respiration, but that you have your impedance waveforms with which to look at the sympathetic side of things with pre-ejection period, for example. So I'm going to move on from there and jump into the application. And again, I'm not really going to talk too much about configuration on the events and modes tab. If we have time during the Q&A portion, we can definitely talk about this in a little more detail. But in general, what I'm doing here is I have a few examples that are set up as events in this file. Events are a way that I can jump directly to a point in time and do some analysis. And so I'm going to be looking at each one of these particular examples, and I'm going to be looking at 60 seconds post each one of them. So we're going to be looking at 60-second segments today. And again, that's what I recommend the segmentation is that you use. And before we actually hop onto the analysis screen, I want to talk about a couple other settings on the screen. So on the HRV calibration settings, we have these frequency bands, which are related to our determination of high frequency heart rate variability. In particular, the one that most people are interested in, the one we're going to be talking about today, is the high frequency / RSA band. And by default, these values are what we would recommend using for adult populations. So there's really no need to change any of these when you're coming into the application by default. You'd only really change these if you're going to work with children, for example. There are some different values that we'd recommend here. And then on the RPeak and artifact settings tab, there are a few settings that are related to the various ECG processing steps that I mentioned in the PowerPoint. So up top, we can see these artifact detection algorithms that we're using. So these are the algorithms that we're going to use to help us identify beats that we may have identified incorrectly or beats that we may have missed identifying. And the two are the IBI min-max check and the MAD-med check. So IBI min-max is very simple. We have a maximum and a minimum heart rate threshold, and we want to flag a beat as potentially artifact anytime we exceed either one of these bounds, whether we go below 40 or above 200. These are programmable, so you can change them if you're expecting your heart rates to go above or below these values, but this is just the default. And then we also have the MAD-med check, which is basically looking at beat-to-beat timing and considering whether it's physiologically plausible when considering all of the beat-to-beat timing within a given segment. There's a great paper that describes this in detail if anyone's interested. That's where I'd recommend you check it out. But this is going to be one of the algorithms that is influencing how we identify peaks. And then the next section that is pertinent to the ECG processing would be the filters that we have to choose from. So there are two filters that we can apply in the HRV application. The baseline and muscle noise filter is really, its main purpose is to flatten out the ECG. So sometimes if you're collecting ECG in an ambulatory environment, you'll see some movement in the waveform, and that can just put more burden on the peak detector to find those peaks. And by turning this on, we can remove that baseline drift, kind of flatten it out so that it's centered around 0, and it makes the peak detection job so much easier. And the other end of that, the muscle noise. So because that electrode is on the right clavicle, it can sometimes be placed over the pectoral muscle, and we can see some muscle activity depending on what's happening during the session get coupled onto your ECG waveform. And when that happens, we'll see this high frequency noise show up again, can disrupt peak detection, so we can filter that out pretty easily using that filter. The next one is a notch filter. So the other most common noise that we'll see in ECG is interference from electrical equipment in the lab. And that presents itself as 60 hertz noise in the United States or 50 hertz noise in much of the rest of the world. And by applying this filter, we can remove that information. So just really quickly, I can show you an example of what this baseline and muscle noise filter is doing. If I just turn it off and click Analyze, and we take a look at this signal, we can see that it's really moving all over the place. It's starting at a lower amplitude, and it sort of has this very low frequency trend that is causing it to approach 0 volts as we go through the segment. And we can see this as we look through many segments, this movement. This is a file that was collected in an ambulatory setting, and it sometimes happens. If we apply the baseline and muscle noise filter, we can see that now we've essentially flattened that waveform out, like I mentioned. And makes it so much easier for the peak detector to find peaks when they aren't varying in amplitude from one another so much. And so that's why we almost always recommend applying that filter and applying the notch filter only when you see 60 hertz noise in your data. Okay, so to demonstrate that, I clicked Analyze, which brought us to the analysis screen. And this is where we're going to see the transformation that we take from ECG to our statistics represented here in these various waveforms. And this is also where we're going to be seeing the point distribution, the points that are flagged as good versus a potential artifact. And we're also going to enter the ECG editor from this screen to actually do our edits. I'm going to expand this so that everyone can see it a little more clearly. So before we jump into the editor, I want to talk about a few things on this screen. And again, we're using the MindWare tool for this, but these same sort of transformations should be happening in any tool that you're using to analyze ECG for high frequency heart rate variability. So the top graph right here is the ECG waveform, and we can see that the R peaks are being flagged either with blue or yellow dots. If we zoom in here a little bit, which I can do by selecting the zoom tool in the lower left-hand corner and picking the horizontal zoom, and then left-clicking and dragging and zooming in. We can see some of the characteristics that I showed you earlier on that sort of perfect rendition of an ECG cycle. We can see Q, small negative inflection before the R peak, which is being flagged, and then the S wave as a negative inflection following it, and then the T wave as this sort of slow, rounded characteristic following the R peak. And we can see that on a cycle-by-cycle basis. These are the sort of things that we're going to be looking for when we're determining whether we have good data or whether we need to do some editing. Okay, so I mentioned there are a few different colored peaks here. So blue peaks essentially mean that once the peak was identified by the peak detector, it passed both of those artifact detection algorithms. So it passed the IBI min-max check and it passed the MAD-MED check. Yellow means that it failed one or both of those. And when that happens, that's when we want to open our editor and we want to look a little closer and figure out exactly what we might need to change. There's one color that hasn't been represented here yet, and we'll certainly get there once we do some editing, and that is orange. And orange peaks are estimated peaks. And we identify those differently from the other two because of that 10% rule, because we have to make sure that we never insert more than 10% of those throughout our entire data file, or each segment, and then certainly throughout the file. So once we have our ECG, we have our IBI series below that. That's the timing between each one of these peaks. And this can actually also be a useful tool for identifying artifacts, and we'll find an example of that here shortly. But before I get too in-depth to talk about the rest of this processing chain, I really want to talk about editing, because oftentimes when we come to a segment, what we're really concerned with are these indications of artifact as represented by a yellow peak, and then what do we do about them? And we're not going to do anything on this screen. We're actually going to have to open up the Edit Rs tool to address these. So I'm going to do that right now, and we'll walk through how to correct this particular segment. Go ahead and maximize that. So when we're in our editor tool, we can see that the toolbar across the top changes quite a bit, and it contains all the various tools that we'd want to use to manipulate the peak locations on this waveform. So we'll want to do things like inserting missing beats. We'll want to do things like deleting erroneously marked beats. We'll want to insert the estimates. We may want to do this on multiple beats at the same time. There are tools that allow us to do all of those things. And the first thing that we're going to do when we come into the screen, typically speaking, is we'll want to zoom in to the areas where we see some sort of artifact being identified so that we can see it a little more carefully. And we're going to do that by, again, selecting our zoom tool. These tools are basically available on every single graph that you see in the application. And we're going to select the horizontal zoom tool. I'm going to click to the left of this area where we see artifact, drag my mouse to the right, and unclick. And we can see everything with much more clarity now. So what we can see in the beginning of the window here is a completely valid, actually beautiful ECG cycle. We can see the P wave, QRS complex, and the T wave afterwards. And we can even sort of see that here, but we can see it starts to get a little noisy. And then we can see that right here, but we can see that it hasn't been identified. And that's because of whatever motion artifact occurred following it being higher in amplitude and close enough to an ECG that it was actually flagged incorrectly by the peak detector. And then we can see after this noise that we can see a clear ECG signal again that has been marked properly, and then again and again and again throughout the rest of this particular window we're looking at. So in this situation, we need to do two things. We need to remove the erroneously flagged beat because we know this isn't an R peak. And then we need to insert it on what we can clearly see is the R peak. And we're going to do that by using two different tools. First, we're going to select our delete tool. And that can be chosen either by clicking this red delete button or by hitting the D button on the keyboard, which is a little hotkey. And when we select that tool, we can see that our cursor changes to this red dotted circle. And this dotted circle could be made bigger or smaller by using the scroll wheel on the mouse or by dragging this sensitivity bar right here. And what we want to do is we want to make it appropriately sized so that we're deleting the points that we want to delete and not deleting points that we don't want to delete. And so I'm going to move my red dotted circle so that the erroneously marked point is in the middle of it, left click with the mouse, and it's deleted. Great, so we removed one yellow peak, but we still have two more. And we can see here that the timing between these peaks is quite a bit more than what we've seen in previous or subsequent beats. But we can also clearly see that there is a beat present right here that wasn't flagged. And so now we need to insert that peak. I'm going to switch to my insert tool. And now you'll see that the dotted circle has changed to white color. And I'm going to do the same sort of thing. I'm going to make it so that the peak I want to insert is inside the circle. Click my left mouse button and it's inserted. And now I can see that that peak has turned blue, meaning that it is now past all of the artifact detection algorithms that I have turned on. So this is going to be done in real time. As you edit, every peak that you add or remove is going to prompt the application to rerun those artifact detection algorithms to make sure that what you're doing is now fitting within those criteria. And so we can see that it's blue, and we can move on to anything else we need to edit in this particular segment. So before we do that, I want to call attention to one other area of this screen that's really helpful when we're doing editing, and that is the point distribution statistics at the lower right-hand corner. So we can see here, the application is telling us how many peaks we have in the segment that are flagged as good, meaning they pass the artifact detection algorithms, estimates, or potentially artifact. And so even though we're zoomed in here, even though we can't see any yellow peaks, the application is still saying that some yellow peaks exist somewhere within the segment. And so we'll want to obviously go to that location and correct them. So when we're zoomed in like this and we can't see them, the best thing to do would be to zoom out. We can do that by selecting that same zoom tool, but then choosing the one in the lower left-hand corner, which lets us zoom out completely. And then we can see that there are some yellow peaks later on in the segment that we still need to correct. So just like before, I'm going to choose my horizontal zoom tool. I'm going to zoom in and take a closer look. And again, we can see here that the noise that existed in this time period led the peak detector to choosing the wrong peak, but we can pretty clearly see what the right peak should have been. So it's a simple delete the bad one, insert the correct one scenario again. So I'm going to delete this and then insert this R peak here. Now we can see, even though we haven't zoomed out, that 100% of our peaks are now passing the peak detection, artifact detection algorithms, and that we don't have any that are remaining that are yellow. So zoom back out, we can confirm that. And then as soon as I close this editor window, I'm committing my edits. And so you want to be sure that you've done the proper edits at that point when you do that. You can always come back in and change them again, but generally speaking, we'll want to make sure that we're ready to commit them when we close this window. When I do that, we can see that all those edits have been reflected on the analysis screen, and we're good to go ahead and save these edits and write them out to our output file if we're doing that. We can save our edits at any time by just hitting Control S or going to File Save and hitting the Save button. And then you can see at the top of the screen that we're currently writing to an edit file. So that was a pretty basic example. Most of this segment was really great, and there were just a couple portions of it where some motion artifact tripped up the peak detector. Simple corrections, we were able to fix it. Okay, so in this second scenario, everything looks good. We have blue peaks all throughout. We can see that per the application, 100% of them are passing those algorithms. But I also see this large motion artifact taking place at around 908 seconds. And when I see this sort of thing, generally speaking, I like to at least zoom in and look at it, because it's possible that there may be still some incorrect placement of R peak on that noise section that is within the appropriate timing, but still not exactly correct. And so I can do that just by selecting my horizontal tool, zooming in here, and of course we can see now that this QRS complex is very obvious on this motion here, and so it is in fact placed correctly, and we can write our statistics out and move on to the next segment. Okay, so same situation here. We have some data that looks a little odd from this far out, but everything's being flagged as a proper R peak. So we should at least zoom in just to make sure that that is the case. So horizontal zoom tool, dragging across, and here we see that that's not the case. Here we see that even though this peak meets the timing criteria, it's very obviously not on the actual R peak. And that's just because of this motion artifact tripping up the peak detector. And so in this situation, if we would have just been looking at blue peaks and we weren't looking at abnormal signal morphology at all, we might have missed this. It's likely that it doesn't have a substantial statistical impact in this scenario, but it's always better to correct these things when they do happen. And so in this situation, we want to open our editor and make that change. One other thing I'll mention before we do that is where the IBI series can actually be helpful in identifying artifact like this. So even though timing was met, even though it passed both of those algorithms, in the IBI series, we can see this very sharp change in interbeat interval, the timing between each one of these subsequent beats, as reflected by this very sharp line where everything else was sort of rolling. And generally speaking, IBI changes are going to be these sort of rolling, sort of slower changes in this waveform, and these sharper changes are less common. So we can actually use the IBI series also as an indicator for when we need to possibly correct a situation like this. So opening up our editor, again, I'm going to zoom in to that point of interest. I'm going to choose my delete tool and delete this. And then I'm going to choose my insert tool and insert this. And I just want to clarify something really quick. These changes that I'm making right now do not contribute to the 10% threshold. So the 10% threshold is only applicable when we're estimating beat locations. When we're doing things like this, we're actually identifying the proper location of beats. So it doesn't matter if a signal is incredibly noisy and a bunch of erroneous peaks were identified and you had to delete them all and insert the correct ones. As long as you can see very clearly where the peak occurred and you're confident about it, and so it's not an estimate, there's no real reason to track how many of those edits you had to make, because they won't have any negative statistical impact on your data. It's only when we're estimating, when we're really making our best educated guess as to where a beat may have occurred, that we have to consider how many of them we've made. But you can do as many of these sort of edits as you'd like without any concern. So again, it would be best practice to just kind of take a look at where we see these abnormal changes in amplitude here, just to make sure that things are working properly. In here, it definitely seems like they are. So in this situation, we would be good. We would save our edits, write them out to the Excel output file, and move on. Okay, so here we see maybe a bit more noise. We definitely see a huge increase in heart rate. We jumped quite a bit ahead in the file for this example. We're out at 3,000 seconds, so almost 2,000 seconds later than what we were looking at before. Some sort of exercise paradigm is taking place here. We have a very high heart rate. So with those sort of situations, generally comes more motion artifact because people are moving around, they're doing something, leads are being jostled, and so you might expect to have to do more editing in those situations. So just like before, our initial approach is no different. We're going to click on this Edit Rs button, and we're going to take a look to see what's happening here. So I'm going to grab my horizontal zoom tool, and I'm just going to zoom in on the beginning of the segment. And so here we can see at around this point that our peaks start to become pretty regularly visible, and they continue to be that way throughout the rest of the segment. But then there's this period of time in the middle here where it's really hard to tell an R peak from the noise that is sort of completely disturbing it and making it just blend in with the rest of the noise. So in this situation, you could do a couple things. You could either estimate the location of these beats, and that wouldn't be entirely invalid, but there's something we can do that's even better that doesn't require any estimation at all. And that is just removing the beginning of this segment where this noise exists. And we can do that because we're looking at 60-second segments. So remember, the other rule that we talked about was we need to have at least 30 seconds of contiguous data to accurately measure something like RSA or high frequency heart rate variability. And when we look at a segment that's as low as 30 seconds, well, we can't remove any data, because if we did that, we'd be exceeding that threshold and we couldn't report those values. But looking at a 60-second segment, we now have the freedom to delete data in the beginning of the segment or the end of the segment and still report the values that we learned from that segment as indicative of what happened during that period. And so that's the easiest thing to do here, and that's what I'm going to recommend we do. So I'll just show you how to do that. And we're going to do it by using these vertical blue cursors. So I'm just going to go ahead and drag this high cursor off to the side, and we're going to be working mostly with this low cursor. And by low cursor, I mean the cursor that's farther to the left of this plot. And I'm going to drag it until it's on the right-hand side of this noisy section. And then I'm going to use some new tools in our point editing area up here to mask delete all of these peaks. So we can see here that under the X cursors section, we have the ability to insert or delete points based on the location of these cursors. And there are arrows on these buttons that indicate where in relation to these cursors we're performing that action. So by default, we're going to be deleting or inserting points between the X cursors. But it's possible to modify that operation by using the Control or Shift keys. So if I hold down Control, I can see that the appearance of this button changes so that there are only arrows pointing to the left. And what that means is we're going to be deleting all points that exist below the low X cursor, so that cursor I just moved. So if I hold down Control and I click this button, we can see that we've deleted all of the points that precede what we are saying is the start of good data for this segment. And by doing that, we can also see that we've removed all instances of artifact for that segment. If we zoom out, we can confirm that. So again, this sort of thing is completely acceptable to do as long as we, at the end of the day, end up with at least 30 seconds of data in this window. And again, that 30 seconds is based off of the number of respiratory cycles that we want to see, with 5 sort of being the minimum and 10 being ideal. And this is particularly pertaining to respiratory sinus arrhythmia. So we can remove data from the beginning and we can remove data from the end, but we can never remove data from the middle. And the reason for that is, again, back to that rule, we need 30 seconds of contiguous data, not 30 seconds of data overall. And by deleting this data in the middle, we're basically creating this incredibly long interbeat interval between these two peaks. And that's going to be interpreted as an increase or decrease, depending on exactly what happened, in variability for the segment, and it's going to skew our results. So we would never want to do anything like this. And when there's noise in the middle of a segment, we're going to need to use that midbeat function to correct for it, the estimation function. So I'm going to hit Control Z to undo that edit. You can always undo or redo any edits in the editor until you commit them by closing this window. So just keep that in mind. If you ever make an edit you don't want to keep, Control Z will get you back to where you started. But generally speaking, that's all we'd have to do for this segment. Everything else looks okay. If I hit the X button, we're back to the main screen. We can see that everything looks all right. And we can proceed to the next segment. Okay, and here we can see that we have a couple instances of artifact that we need to correct. We can see in the IBI series, these spikes that I mentioned before are indicative of something that we might need to change. And so we just open up our editor to take a closer look. Again, choosing my horizontal zoom tool, I'm going to click to the left of the noise, zoom in, right click. And here we can see the correct morphology of ECG leading up to this point where there's clearly something missing, and then correct morphology of ECG from that point forward. In this situation, there's nothing in this time window between these two yellow peaks that clearly looks like ECG. We could see examples of it on either side of it, but we can't see anything in the middle. And this is when you would have to estimate its location. using the midbeat tool and using these cursors. So to do that, what I'm going to do is take my high blue cursor and drag it by clicking on it and holding on the mouse button and just dragging it to the right of the last known good beat. And then I'm going to take this low X cursor and drag it before the first known good beat. So it doesn't have to be like anywhere close to this peak. It just needs to be between these two peaks. We're basically telling the application that these are our good peaks and there's something missing in the middle and we need to estimate it. So when we do that though, we'll notice that the midbeat tool, which was previously grayed out and unavailable, becomes enabled. And by midbeat, what I mean is we're going to place a beat in the mathematical center between these two known good beats. So right in the middle of them. And if there were more beats missing, then we would be just splitting that interval into equal increments. So if there were 2 beats missing here, we would see that the application recognizes that 2 beats are missing, and then they would just be placed equidistant between those 2 known good beats. When we do this, I'm just going to hit the midbeat button, and we'll see that a peak was inserted that has no relationship to the actual waveform that we see here. And that's by design. We're not using any characteristics of the waveform to determine where this point is placed. All we're using is the timing of what we've determined are the 2 good beats surrounding this area of noise. And so it's not going to be placed on any particular location on this waveform. It'll be placed at 0 volts, and it'll be placed right in the middle of these 2 points. So we'll notice that there are 2 things about this peak that are interesting. One is that it's blue. That means that by inserting this midbeat, we have restored the timing criteria as dictated by those artifact detection algorithms. And it also has an orange cross around it. That means that it's an estimate. And we can see it reflected down here in our point distribution. We can see that we have estimated 1 beat, which contributes to 0.7% of the total beats of this segment. So at this point, we're well under our 10% threshold. This is where that threshold comes into play. You'd want to watch that we don't exceed that. And that's it. That's what you would do when you can't tell where the R peak would have occurred, even though you know there should have been one. Stepping back for a second, we can actually click on these peaks to help us identify what kind of edits we need to do. So by left clicking on the peak in the editor, we can actually see both of these point checking algorithms and which one it failed and the reason potentially for why it failed. Now, these reasons are not always correct. It's sort of our best guess based off of the algorithm, what it might have been. And in this case, though it is correct, the MadMed algorithm is returning that this is a long beat, which would mean essentially that there's probably some beat missing in the middle. And so inserting the midbeat confirms that yes, there should have been something there. And by inserting it, we can see timing is restored. I'm going to zoom out because I remember that there was something else here I needed to fix. And again, just kind of zoom into that section and take a look. And so we have another example here of really being unable to identify where in this noise the ECG signal is buried, where our QRS complex is. And so in the situation, again, we want to do a midbeat. I would simply move these blue cursors so that they're on the outside of the known good beats, hit the midbeat button, and we can see that timing is restored. And now we've midbeated a total of 2 beats, which accounts for 1.4% of our total point distribution. Totally acceptable, well under that 10% threshold. And we can be confident then in using these values. And so I just committed my edits, hit Control S to save them. And here we are with our statistics ready to be output. All right, so now we've covered in this first file examples of when we want to delete erroneously marked beats, when we want to insert beats that we clearly see but have been missed by the peak detector. And we've shown also what happens when we can't see the peak, but we know that there should have been one there and it was obstructed by noise. We use that midbeat. I'm going to close this file and I'm going to open another example that will illustrate another scenario that you'll probably find yourself in at some point. and that is when there is some sort of cardiac arrhythmia or abnormal beat, which again requires us to do estimation, but our indicators of that are a bit different. So I'm just going to open that file up. I'm going to leave the channel mapping as is. We're going to be looking at subject 1 in this file. And then I'm going to jump directly to segment 1, which is going to illustrate this for us. So I'm going to switch to event mode. I'm going to remove that first event, and we're just going to look at this one segment. I'm going to hit analyze. All right, so we see a few things that look a little odd here. First one is this sort of change in amplitude here, but if we zoom in, we can see that, yeah, this looks pretty much like a normal QRS complex. But then if I zoom in to this beat right here, we can see what appears to be normal cardiac cycles leading up to it. Again, beautiful P, QRS complex, T wave afterwards. But then we get to this beat at around 389 seconds that clearly looks different than the others. There's an absence of a P wave, there's a widened QRS complex, and then there's still a T wave, so that's fine. And then we can also see pretty clearly that the timing has changed substantially between these two beats and between the next two beats. And so in this situation, even though the application is correctly finding an R peak, it's not an R peak on a QRS complex that was driven by a normal cardiac cycle. This is some sort of cardiac arrhythmia, an abnormal beat. Generally, people will have these. It's not that uncommon. They're most commonly benign. And so there's no real concern for the subject's health or well-being necessarily, but there is certainly concern when it comes to editing for high-frequency heart rate variability, because we don't care to quantify variability that's driven by abnormal beats. That's some sort of cardiac condition, some physiological abnormality. It has nothing to do with control from the parasympathetic nervous system, which is what we're really trying to quantify. And so in these situations, we actually need to remove these beats, remove their influence from our statistical outputs and midbeat them, just like we would if we couldn't see the R peak. So to do that, I'm going to open up the Edit Rs window. I'm going to zoom in on that section. And first, what I need to do is delete this ectopic beat, this abnormal beat. And I'm going to do that just by choosing my delete tool, hovering over the peak, clicking the delete button. And then I'm going to use, again, my blue cursors to go on either side of this abnormal beat. And we can see that there is, in fact, supposed to be a beat there. The application sees that. And when I hit the midbeat button, it's going to just place it right in the middle. Again, completely ignoring any waveform characteristics here because we don't care. We just want to place it mathematically at the center of these two known good beats. And by doing that, we've restored timing and we've removed the influence of this ectopic beat. So just to reiterate, when we get to this point, we're looking at extreme changes in beat-to-beat timing, which we certainly saw here and which led to this point being flagged by the MAD-MED algorithm. And we're looking for abnormal characteristics of the waveform. So the absence of a P wave is going to be an indicator. If you're seeing P waves in other situations and you're not seeing it for this particular complex, P wave being that positive inflection before the QRS complex. A widened QRS complex, so a longer interval between Q and S will be indicative of these abnormal beats. And then oftentimes you'll also see a shortened QRS complex with a higher amplitude T wave, which I also have an example of that I can show in a moment. We're not using these to identify specifically what the arrhythmia is. Most of the time, we're not trained in identifying those arrhythmia, and additionally, we're only looking at a lead 2 configuration of our ECG. So we would need to look at multiple perspectives on the beat, on the heart, to really identify this is what the arrhythmia is. But it's not important for us. We don't care what it is. We just care that it happened and that we're removing its influence from our statistical output. So we want to go through and find the second occurrence of this arrhythmia. That's another thing we're going to see commonly when we have these sorts of segments is they're going to happen over and over again. you're going to see them throughout a segment, throughout a participant's file. And that's another indicator that you are dealing with some sort of cardiac arrhythmia and not just some abnormal morphology or noise. In this situation, I'm going to hit delete it again, move my cursor so that they're on either side of the known good beats, hit the midbeat button, and again, we can see that we've restored timing. In this situation, we've only corrected 2 beats here, so we're at 2.6% of our total beats in the segment, and by that we can be okay with these edits. Zoom back out to make sure that nothing else needs to be changed, and commit them. Now, depending on the severity of the arrhythmia that you're experiencing, this is one way in which you can pretty quickly start to exceed that 10% threshold. So just make sure that you're always watching that to make sure that you aren't. And so I think if I come back to my events and modes and I just look at this in 60-second segments, there is an example of another style of arrhythmia that would be interesting to show. Yep, here we go. So if I zoom in on this portion of the segment, we can see what I mentioned before, which is an enlarged T wave and a shorter QRS complex. And when this happens, coupled with the change in timing, we can feel pretty confident that this is some sort of arrhythmia and that it needs to be corrected. And so again, we would come into our editor, zoom into that section, hit our delete button, move our cursors so that we're looking on either side of that ectopic beat, hit the midbeat button, and we're good. And here we can see that there was one actually right before it as well, so I can also midbeat this. And then there was one other ectopic beat in this particular segment. This looks more similar to what we were seeing on the other segment, which was the widened QRS, the absence of a P wave, but same sort of technique would apply here. You would just delete it, move these cursors so that they're around the good beats, hit midbeat, and then you're done. Okay, so those are sort of the main scenarios that you're going to find yourself in. Of course, you're going to see these in varying degrees of severity. So what we looked at mostly today were good segments with some areas of noise. There are going to be plenty of segments that you look at that will be more noise than in good signal. And so it will require you to go through in detail, zooming in and looking cycle by cycle and identifying the ECG signal. As long as you follow those rules, the 30-second rule and the 10% rule, doesn't matter how many inserts or deletes you have to do to accurately identify those R peaks, just do as many as you need to. We're not going to track those, and just always be aware of how many beats you're estimating. And when you have to discard a segment, hopefully that is one segment within a larger analysis period. So let's say you're looking at a 10-minute baseline and you have 2 segments that you need to discard. You can take the average representation of those other 8 minutes as indicative of your baseline and still end up with values to compare to later down the road. So that would be the appropriate approach there. All right, so I'm going to switch back to my slideshow because we're coming up on the Q&A section, and I'll switch screens here. So before we get into Q&A, and I'm just going to take a moment to look through the questions that you've already asked to kind of get them ready to be answered. Of course, feel free to keep asking questions as I'm answering what's already been asked. I'm happy to go for the full 30 minutes here answering anything that can be helpful. But I did want to mention before we go that we are finally having our first in-person seminar and workshop in over 2 years. This has been postponed twice, unfortunately, due to the pandemic, but we're getting to a point where we feel comfortable running the event, and it seems like many of you are going to feel comfortable attending, so we're going to give this a shot. We're going to be doing it in Salt Lake City on April 8th through 10th of next year. We're going to be doing in-depth HRV and cardiac impedance acquisition and analysis. So our scientific advisors, Dr. Gary Burnson and Dr. Greg Norman, are going to be presenting. We're going to talk about historical perspectives, We're going to go in depth into the underlying mechanisms that we're measuring, and then we're going to have a hands-on practicum where we collect the data, where we actually go through examples, we analyze it, and one of the best parts about this is something that we've missed greatly, which is the ability to network with researchers from around the world that attend this event. So we'll have our standard networking event with food and drink, and we'll be taking all the necessary precautions to make sure that it is a safe and enjoyable event for everyone that's able to come. So more on this soon. Everyone pay attention to your email. We'll be sending out a newsletter when registration is available, hopefully in the next couple weeks or so. So with that, we'll move on to Q&A. I'm going to take a moment just to look at the questions that have come in, and we'll get to answering them in just a couple minutes. Okay, so we have a question regarding frequency. So I'm just going to touch base again, and we really didn't talk too in depth about this because I wanted to get into the editing examples, but let me pull up the screen again, the analysis screen, and we can talk through what I mean by frequency. So we're looking at beat to beat timing when we're talking about heart rate variability. So variability in beat to beat timing. And we can see our beat to beat timing up here in the blue peaks that are present on the ECG signal. And then we can see the IBI series, which is just another representation of that beat to beat timing. So we have on the y-axis, the actual time between subsequent beats. And on the x-axis, we have the actual beat number. And from there, we want to pull out frequencies from that waveform. So you can think of a frequency as a sine wave, if you're familiar with that type of waveform. A sine wave is a signal that has a pure frequency. It's only a single frequency. But a complex waveform, such as an ECG or an IBI series, is essentially the summation of many sine waves of varying frequencies and varying amplitudes. And that's going to change on a segment by segment basis. It's going to change on a subject by subject basis. And that is basically what we're quantifying, is the presence of certain frequencies in this waveform and their magnitude. So to do that, we have to get from this IBI series to a point where we can extract those frequencies, extract the magnitudes of those frequencies. And the first thing we have to do before we actually do that is some manipulation on this IBI series to get it ready for that type of analysis. And that's what we're seeing here with the heart period time series. So before we run our frequency analysis, before we extract those frequencies, we have to remove the baseline trend from that data, and we have to interpolate it, because it's just a requirement of frequency-based analysis that we have a certain number of samples or data points in our waveform by which to represent those frequencies. So the heart period time series is basically that detrended and interpolated representation of the IBI series. And then we pass it through a fast Fourier transform, which takes it from the time domain, what we see up here, measured in seconds, to a representation of the same waveform, where we're instead looking at what are those frequencies that make up this complex waveform and how strong are they. And from there, we want to drill down even farther and say, we really care about the strength within these specific frequency bands. When it comes to high frequency heart rate variability, or RSA, we're interested, of course, in the high frequency band, which typically is between 0.12 and 0.4 hertz for adults. For children, that'll change a little bit. There is a post on our website that will tell you what you should change those to, and it's in the literature as well. I'll send out a link to that in the follow-up. But essentially what we're looking at here now are the various frequencies that make up this waveform and how strong are they. And we're going to take the power within the high frequency band and take the natural log of that, and that's what's going to give us our RSA statistic. So when I say frequencies, that is what I mean. I mean, we're quantifying the frequency content of a complex waveform, that complex waveform being the IBI series. And we just know from historical studies that the high frequency band when respiration is also present there, is indicative of respiratory sinus arrhythmia, which is therefore indicative of parasympathetic nervous system activity. So hopefully that clears that up. Okay, next question is about trial lengths. So I mentioned earlier that you have to have a 30-second window to compute RSA. And that is true when you're using the spectral method of calculating RSA, which is what I just described, that process. You need to have at least 30 seconds. So if you were going to look at something like a 3-second trial window, you would not have enough beats in that window to effectively quantify RSA. Now, there are other approaches that allow you to get a bit more granular that we don't support in the HRV application because they're sort of complicated and they're not as commonly used. One would be the peak valley approach, which would be where you'd identify peaks and troughs in respiration by hand and look at timing during periods of inspiration versus periods of expiration. And you can use that to also get an RSA type metric. Again, that's not something we can do in our application, but it's something that you could explore. And then we have time domain statistics. So we talked a lot about frequency domain, but if we move the time domain, we can get away with having shorter analysis periods and still getting valid results. In particular, RMSSD, the root mean squared of successive differences, has been shown to highly correlate to the frequency-based analysis of our RSA. And so you might be able to get away with looking at shorter segments, but I think 3 seconds is still going to be too short for that to really be valid. Another approach that you could possibly take, and again, this is still using that 30-second minimum, but in a slightly different way, is in the HRV analysis applications, we have continuous mode, which will allow you to look at sort of second-by-second changes in all of these statistics, including RSA, by using a 30-second rolling window through the data. So imagine the first window is 0 to 30 seconds, the second window is 1 to 31, the third window is 2 to 32, and so on and so forth. And we'll calculate RSA on each one of those segments. So you can sort of identify more rapid changes in these values by using this mode. But again, always remember that it's not based on a moment in time, and it's still not based on a 3-second window. It's based on this rolling 30-second window, which allows us to have enough data points to quantify RSA. And just as a reminder, the recording of this seminar will be on our YouTube channel. Give us a few days to get it all tailored and set up there, and you'll certainly get a link in an email afterwards so that you can rewatch. All right, we have another question about the 10% rule. So just to reiterate that as well, the 10% only applies to when you have to estimate beats. If you are inserting and deleting beats that you know are either incorrect or correct, respectively, then you can do that as much as you want. It's really all about how much data are we guessing at? How much data are we estimating? And we want to make sure that that always stays below that 10% threshold. Okay, so the next question is related to arrhythmias. So the question is, when the patient seems to have an arrhythmia and the R peaks are correctly detected, however, they're detected as yellow stars due to the varying distances, are keeping the yellow stars okay if the R peaks are properly defined? So that basically is just that example that I went over. So if even if you're seeing an R peak identified properly, but you're seeing some other indication of an arrhythmia, whether that's a widened QRS complex or the absence of a P wave or an abnormal T wave, or just an extreme change in timing, most likely what you're going to need to do is delete that R peak and midbeat it. There are going to be instances where valid R peaks are still flagged because there's just an abnormal amount of variability for that particular beat to beat timing. And in those situations, you sort of have to make a judgment call. It's a little muddy in terms of exactly what you need to do. And many people, just for the sake of consistency, especially if there are multiple scorers, would say in those situations, just delete and midbeat it. Don't try to interpret it in any more advanced way. Other people will look at it and say, yeah, this does kind of look like a valid peak and there's just a lot of variability. Maybe that's something you're expecting. And in that situation, it may be correct to leave that yellow peak. But again, there's just not any strict rules that I can give you to really dictate when that is or is not appropriate to do. In that situation, though, another thing that I would recommend checking is that your average heart rate is not coming anywhere near this maximum or minimum threshold for your IBI min-max check. Because sometimes beats can be flagged simply because they exceeded these thresholds and we forgot that we had them in place. And so in that situation, if it just exceeded that threshold, you know, it's probably fine to leave it, and you probably just have to adjust your IBI min-max threshold to allow for beats like that to occur. So just always, if you see a beat, you know, remember you can come in here to the, I want to do that. You can come in here to the analysis screen and click on the beat and see which of these two checks it's failing. And so if it's checking that IBI check, then it's probably fine. It's probably not an arrhythmia. Arrhythmias are going to be almost always caught by the MAD-MED check. Okay, the next question, if adding a midbeat creates an artifact on one side of the added beat, what is the recommended action? So again, this is sort of on a case-by-case basis. There are certain arrhythmias that will result in a reset of normal sinus rhythm. So what I mean by that is when we're measuring an EKG, we're measuring sinoatrial node activity. That's the body's pacemaker, the heart's pacemaker. And it's where the electrical impulse that is basically telling the heart to beat is coming from. And, you know, it's innervated by both the parasympathetic and sympathetic branches. And high frequency we know is purely parasympathetic influence. But all that being said, there are some arrhythmias that will disrupt that rhythm such that from that point forward, everything is different from what came before it. And there are those unfortunate incidents in which they occur in the middle of a segment. And when this happens, you would want to remove data either before or after that arrhythmia completely, so that you're only looking at data either before it took place or after it took place. And as long as you're analyzing in 60-second segments, you know, hopefully that means that you're removing less data than you're keeping, and that would mean that you could still use that segment for your statistical output. But then if it occurs in the middle, or if you're using smaller segments, then you probably just have to discard that segment. And I guess the other situation that could possibly arise there, if you run into that, would be maybe the beat immediately preceding it, or maybe other beats in the segment need to be corrected before timing is considered to be correct. So what I would suggest doing, if you don't think this is an arrhythmia, but rather just noise, is I would do all of your other edits in the segment and then see if that beat is now considered proper timing. The MAD-MED takes into account beat-to-beat timing throughout an entire segment, not just in that one location. So it's possible that by correcting other beat-to-beat timing in other parts of the segment, that the algorithm sort of corrects itself and starts to see that beat as being acceptable again. So those are the two approaches that I would suggest you take if you run into that situation. Okay, so next question. If you have 10 minutes of contiguous ECG data and you have to delete a segment in the middle of the 10 minutes, can high frequency HRV still be calculated because there is greater than 30 seconds on either side of the deleted segment? So if you're looking at the 10 minutes as a whole, so all at once, the answer is no. Because by deleting that middle segment, you're creating this very long period between the two known good data points that's going to be interpreted as a very, very long IBI, and so therefore it would skew our results. And for a number of reasons, we need to just have that contiguous series. So what I would recommend to you if you're looking at a 10-minute period, unless you're wanting to examine low frequency or very low frequency components of the waveform, low frequency is some mixture, some unknown mixture of sympathetic and parasympathetic influence. and it's more commonly used in clinical applications than it is when we're trying to quantify RSA or look at something psychological. If you're looking at low frequency components, then maybe you have to look at 10-minute segments. But what I would rather you do actually is look at that 10-minute period, but do it in 60-second chunks. Because when you do that, then you do have the option of discarding that minute in the middle and not impacting the calculations performed on the other 9 minutes of interest. And so then what you would do is in your higher level statistical analysis, whether you're doing it in Excel or SPSS or R, or wherever you're doing it, you would just take the average representation of however many segments you had from that period as indicative of the whole period. And that one being, the one missing would not require you to discard that 10-minute period. So that would be best practice. And I will send out in the follow-up email some resources. So I mentioned a few publications throughout this presentation, and I'll send out links to those so you can check them out, specifically where it talks about 30 seconds of data and why that's necessary and that sort of thing. So just keep an eye out for that. Okay, this is a fun question. Is it possible to get correct ECG readings on males with chest hair? This is a real problem. Probably not possible for us to get IR approval to shave. Your guidelines on this. So because of the location of the ECG electrodes in particular, being on the right clavicle and the lower left rib, those are not generally areas where there's a lot of body hair present. So ECG is actually the easier one to get. Cardiac impedance is much more challenging, because one of the electrodes goes right there in the xiphoid process where the ribs meet, and that's generally where you're going to find chest hair present on male subjects if you're running into that problem. So in general though, if you need to offset the electrodes slightly to avoid particularly hairy areas, that is possible, as long as you are not offsetting them much, and as long as you're previewing your data before you acquire, to make sure that you're still seeing the expected morphology. So for ECG, you could move it a bit farther over on the clavicle and still have the same vector on the heart. So we're still going to have that pronounced positive R peak that we're using to identify the beat timing in this situation, and that's going to be enough. For things like impedance cardiography, I'll just mention it since I just mentioned it earlier. You can offset it to the left or to the right of those really hairy areas and hopefully get better electrode adherence. Beyond that, obviously some labs will be able to get IRB approval to shave the participants. You might have more trouble recruiting if they know they're going to get shaved, so keep that in mind. But there should be, I would imagine, ways to, with ECG, get clean recordings even in the presence of body hair. Okay, so there's a question about versions. So the question is, the version of MindWare software that this person's using doesn't show the orange cross behind the edits. So that is a new feature in 3.2. 3.2 has been out since early 2018, and it contains a few things that I've gone over today. One of which being the orange cross behind the midbeat, another being the point distribution, so that you can track that 10% threshold as you go through and make your edits to make sure that you never exceed it. The other thing is that this 3.2 will output these editing statistics, which can be really helpful when you're going back to audit data that's been analyzed by undergrads or research assistants, maybe before you're getting ready to do your larger statistical analysis. You can look for any segments that contained midbeats or contained estimations or contained artifacts, for that matter, and revisit them and make sure that the editing was done properly. So that is a 3.2 feature, and it can really come in handy too if you're doing both HRV and cardiac impedance analysis, because in impedance you don't want to have midbeats, you don't want to estimate locations of R peaks, and in HRV you do. And so in the past, when moving from one style of analysis to another, you would have to first insert midbeats in HRV, and then in impedance, you'd have to delete them again. And with the new version, we're able to automatically ignore all of those midbeats. So if you inserted them all in HRV and then you reuse those edits for impedance, you can just click a button, we'll automatically ignore them, and you won't have to do any of that sort of repetitious deleting that you'd have to do in the past. And to upgrade from 3.1 to 3.2, there's pricing available on our web store. You can certainly reach out to any of us at MindWare. We'd be happy to demo the other features for you and talk about what it would take to upgrade. Okay, so another question about what happens if we insert a midbeat and the program still shows the peak is yellow. Again, it's sort of that case-by-case situation. If you're inserting a midbeat and the midbeat still shows as yellow, then it's possible that the application didn't identify properly the number of beats that we're missing. So if I come in here and I zoom in, actually I'm going to go to a section that has some R peaks, and I'll delete them just to help illustrate this. So I'm going to delete 2 peaks here, and then I'm going to say, okay, let's assume that those, you can't see them. Actually, I'll just come in here and remove the data so that we really can't see them. And then I say, okay, I need to estimate location of a beat here. Well, when I do this, because we just saw that there were 2 peaks here, the application's actually showing that we need to insert 2 beats that are now missing. And so if I hit the midbeat button, we can see that timing has been restored, everything's fine. Now, there are scenarios in which maybe you're right on the cusp of what the application would think is a gap that would require 1 beat versus a gap that would require 2. And in that situation, it might think there's only 1 beat that needs to be inserted. If I midbeat there, we can see now that one of these has been flagged as yellow because there's still something funny going on with timing here. So something that you could try, especially if visually it looks like there may be more than 1 beat missing, you can just manually change the number of beats that are inserted and then see if that fixes things. So that might be another technique that you could employ when that sort of thing comes up. But again, just to reiterate from earlier, you want to make sure if it's an arrhythmia that it wasn't some arrhythmia that reset normal sinus rhythm, in which case you'd have to delete all data on one side or the other, or you'd want to go through and do the rest of your data editing before coming back to this instance and reviewing it for correctness or for whatever else you might need to do to it. Okay, and then last question that I have in here today is, what should we do if the first peak in a section is yellow? So if the very first peak in a segment. In that case, you can just delete it. You don't necessarily have all the information you would need before that segment to confirm that it is in fact good or potentially artifact. Occasionally, this will happen just as a result of the artifact detection algorithms seeing something that does look normal. What's good though is that because it's at the beginning of a segment, we're going to be sticking to our rule of only ever deleting data on the beginning or end of a segment and having that contiguous R peak series in the middle. So by deleting that first peak, it's perfectly valid to do it, and then you could trust the stats that you output from that point forward. All right, so we have a couple of minutes left. If anyone else has any questions to ask, please do go ahead and ask them. Otherwise, for those of you that have to take off, thank you so much for attending. We really appreciate your time, and I hope that you learned something today, that you took something away from this. We will be sending out a follow-up survey, so we always really appreciate. One of the things that we changed this time was many of you felt like the webinars were too rushed and you wanted them to be a little longer. So rather than our standard hour length, we went for 90-minute length this time. So the feedback that you provide us, we really do take it to heart. We use it to inform what we do for future webinar offerings. So definitely fill that out if you get a chance. We really, really appreciate it. And I guess another reminder before we take off is not only will this webinar be available on our YouTube channel for review after this is done, but there are a number of resources that can be really helpful after the fact on our support portal. If you just go to support.mindwaretech.com, you can find a ton of blog posts, knowledge base articles, videos, everything on how to use the applications. and some common tips and tricks when it comes to acquiring data, analyzing data. And if you ever feel like you need a more personalized approach, you want to look at your data specifically, we have both complimentary and paid training options that we can provide to you and your lab. You can feel free to reach out to us or visit our support site for more information there. But all right, no more questions have come in, and so we'll go ahead and end for today. So again, thank you so much. I hope you all have a great week and look forward to talking to you all soon. Take care.